Welcome to another multivariable calculus screencast. Today we're going to address Green's theorem, one of our first vector calculus theorems, and we're going to do a particularly nice example where we're going to define winding number for a particular curve. Let's remind ourselves of the statement of Green's theorem. It relates a line integral of a vector field over a simple closed curve to a double integral. So C here is that simple closed curve oriented positively, that means counterclockwise. We've got a vector field whose components P and Q are continuously differentiable everywhere. So there's our vector field with a bunch of arrows there. But I want to focus on that point in the interior. That means that those dq dx and dp dy have to be continuous on the whole interior D. That part right there is we're going to use to see our interesting application in winding number. So let's ask a question about that region D. Does it really have to be what we call simply connected? It's a solid region without any holes in it. And it turns out the answer is no. We can still apply Green's theorem to something like this. All right, we've got our domain D here in blue, and we see the boundary positively oriented, which means counterclockwise on the outside. But then we actually can allow piece of the boundary on the inside, right, a hole in our domain, if you like, as long as it's oriented the opposite direction. All right, so this is still the boundary of our region D, but it has to be oriented the opposite direction. And if you want a rule that connects these two ideas, you could imagine standing on the surface, on the plane here, walking in the direction of our boundary point, as long as the interior is always on your left. Right, then we're positively oriented. So on the outside, that means counterclockwise, and on the inside, since we're walking this way, right, imagine standing on top of this plane here, again, the interior will be on our left. So that's the unifying property here. So the boundary is positively oriented if the stuff is always on the left. And it turns out we can apply Green's theorem to a domain like this. It looks exactly the same. Just now the integral around the outside is going to encompass both parts, counterclockwise on the exterior, clockwise on the interior. And we can see that quick visual proof of why we're allowed to do that comes from just splitting this domain up into two pieces, sort of an upper and a lower. So what I've done here is we've taken the same domain and just cut it into two pieces. And then we consider each one separately. So our double integral, of course, is the sum of the integral over the two parts. Right? And we can apply Green's theorem to each part individually, right? The top and the bottom. And so when we apply Green's theorem to both of these, look what happens. We get a line integral around the boundary of each region, which means it's going to be going one way to the right from the blue side over here, and to the left from the red side on this common sort of cut of the region here, right? The two regions share this boundary, but it's traversed in opposite directions for the two line integrals. So they cancel out, and all you're left with is a path that goes around the outside, right? You see to the left for the blue part, and then to the right down here for the red part. So there's our outside curve. And on the interior, we're just going the opposite direction. Right. To the right, up on top, and to the left on the bottom. That's clockwise. So you can easily see that adding the two double integrals will give us the integral of the whole region, and adding the two line integrals will just give us the boundary curves. Outside counterclockwise, inside clockwise. So now let's look at this cool example. Now it focuses on this very specific vector field that we see defined up here. So this doesn't apply in any way in general, but it's just an example. So we look at this vector field. First, we've got the scalar 1 over 2 pi. That's a scaling factor that'll come up later. All right, but let's look at its important properties. First, we see that we've got minus y over x squared plus y squared and x over x squared plus y squared. So they have that common denominator, x squared plus y squared. And we should probably think of that as r squared, right? The distance from the origin squared. So this vector field scales like 1 over r squared. So we see that its magnitudes are bigger toward the origin, right here, and they get smaller as you move away from the origin, right? we divide by a smaller number there. In fact, they're undefined at the origin. That's going to be key here. Now, I omitted graphing any of the arrows near the origin. They just get too big around there. But in particular, notice this is completely undefined. This has no value at the origin. The rest of the, as far as direction is concerned, we see that it is rotational. We have minus yx in the numerators up here. And so, right, as we move up, the vector field points left. As we move down, it points right. And of course, up and down, we see this kind of circular motion here. So you can certainly see what the flow lines would be of this vector field. You certainly just move in a circle, right, around the origin. But it's funny that it moves kind of faster toward the center, right, and slower when you get farther away. Vortex action here. So let's look at what line integrals do here. All right, so we're going to look at a few in particular and start with something simple, like let's just move around the unit circle and compute our line integral. Note something very carefully. The line integral itself along the unit circle exists. Right? The vector field is perfectly smooth near there, even though it's undefined at the origin. If our curve never hits the origin, the line integral is perfectly well defined. So let's watch what happens as we move around the unit circle. This number on top will compute the line integral. We've got a small piece of it right now. As we move around to the y-axis, we see we get 0.25 there, and we keep going. Right. We hit 1/2, halfway around, interestingly, so you probably know where this is going. When we complete a full circle, turns out that that line integral is exactly 1. Right, so one trip around the unit circle leaves us with a value of 1. To see why this is interesting, let's see what Green's theorem has to say about this vector field. We saw that that integral around the unit circle, the line integral, gave us a value of 1. To see what Green's theorem has to say, we need to know what the partial derivatives are of fr, and that's a straightforward computation. We just need the quotient rule here, so dq dx, we differentiate at 1 for the derivative of x times the denominator minus x times the derivative of the denominator, which is 2x, all over x squared plus y squared squared. If we neaten that up, we just get the difference, y squared minus x squared, in the numerator. And that basically r to the 4th in the bottom. Switch over to the p component, and we do the same thing now. We see a minus y there, so we get a minus sign. And then we do our quotient rule. Now neaten it up with the minus sign. Lo and behold, we get exactly the same expression. So how is that relevant to Green's theorem? Well, remember what the integrand in the double integral of Green's theorem is. It's that magic dq dx minus dp dy. And here we're finding that it's 0. So already we see that there's something funny going on. We have an integrand in Green's theorem that gives us 0, but we have an integral around a simple closed curve whose integral is 1. How could it be 1 if the integral over the interior must be 0? Well, the secret lies in that in its interior thing. Notice that our vector field is not continuous. Right? It's not even defined entirely on the interior of this curve. We've got that origin. That's the only problematic point. Curve smooth everywhere else, but just that one point is enough to blow up Green's theorem. Right? So we get 1 when we integrate around the outside, but we can't even do the double integral on the inside because p and q are not defined there. Right? But interestingly, dq dx is minus dp dy is 0 everywhere else. That's not the end of the story. Turns out we can exploit this to see something very cool. So what can we do with this? Well, as is often the case in mathematics, what looks like a bug turns out to be a feature. Recall that we're allowed to apply Green's theorem to our domains with holes in them, right, provided the boundaries are oriented properly. So here I've got a region, right, with a hole in it, and we basically cut out the origin. That's the neat thing here. So we're going to imagine that this little hole in the middle is small, right? We're going to say it has radius epsilon, right, to indicate that it's a small number. And we've got some curve on the outside. It looks like kind of a starfish here, but it could be anything whatsoever. So let's label the outside curve C1, and I'll label the inside curve C2. Notice they're both going counterclockwise. Now what Green's theorem says is that the integral along the boundary curve, but going counterclockwise on the outside, so that's the integral C1 of f dot dr plus the integral going clockwise on the bottom, so that would be subtracting the integral C2 as I've labeled it here. Right. So that if we do that computation, we should get the double integral over the interior of qx minus py dA. So we're just looking inside here. And notice that p and q are perfectly smooth inside here, so this integral is going to converge, and in fact, it converges quite trivially. The integral is 0 everywhere, so this thing is 0. Okay, so that helps us quite a bit, because now look at these, means these two pieces of the line integral, the outside C1 and the inside C2, must cancel each other out. They're of course equal, and that's the profound idea here, that if we take a curve going around the origin, f dot dr, it turns out to be exactly the same as a curve of any size, right, of any circle going around the origin, no matter how small. Right. And these are closed curves. So this idea will work absolutely any simple curve, right, where the origin is on the interior. We'll always be able to find a small circle to sort of carve out, and we can repeat the same experiment. And that's the very profound idea here, that any curve whatsoever, star-shaped, blob-shaped, it doesn't matter. If it encircles the origin, I can find out that its integral, its line integral through this vector field, is the same as going around a small circle around the inside. Now we need to compute that number to make this make some sense. Now let's compute that line integral on the inside here on the chalkboard. So we've got our special vector field here. I pulled out the 1 over x squared plus y squared term. Now our curve is, of course, the circle with little radius, epsilon, oriented counterclockwise, the way we set this up. We know how to parameterize that. R of t is epsilon times cosine sine. We'll do it where, of course, t goes from 0 to 2 pi. All the ingredients we need for a line integral are here. Let's just put it together. So the line integral around f dot dr, we translate into a t integral. So the bounds of integration are going to be 0 and 2 pi. I get 1 over 2 pi. And then do notice here, and this is important, that x squared plus y squared for this curve is naturally just epsilon squared times cosine squared plus sine squared, right here, which of course is 1. So we just get the epsilon squared down here. That's why we bother doing this around a circle. We get this really nice form for the vector field. Right, this scalar term here is just given by the radius squared. Then we proceed, all right, so let's continue evaluating f. Here we just plug in epsilon cosine, epsilon sine for y and x. So there's the f term along our circle. And it's epsilon sine t and epsilon cosine t. What's next is, of course, the derivative, the tangent vector that comes from here. But lo and behold, when we compute that, right, we get exactly the same vector, minus epsilon sine t, epsilon cosine t. And we integrate with respect to t. Now things start really coming together. We simplify. That scalar stays, and notice now I've got a vector dotted with itself. That's its length squared. But its length squared is epsilon squared. So of course we just cancel out the epsilon squares, and now we've got a constant. This is rather easy integral to do, 0 to 2 pi, 1 over 2 pi. 2 pi's canceled. This is just 1, and this cancellation is key here. It doesn't matter what the radius is for this vector field. We always get 1. So what have we learned if we put this all together? Well, we've got this supremely beautiful fact that not only is every circle around the origin going to give us an integral of 1 through this vector field, right, but because of that trick of Green's theorem, if we integrate around some other strange shape, we're going to get 1, provided it goes around the origin. Also due to Green's theorem is to see what happens if we don't encircle the origin. So let's take a curve here that moves around. It's going to be closed, all right, but stay to the right of the y-axis. This does not encircle the origin, and now we get 0. Again, straight up Green's theorem, this line integral must be equal to the integral on the interior of qx minus py, which we saw that was 0. So this is really cool. If we take a curve that does not contain the origin on the interior, we're going to get 0. If we take a curve that does contain the origin, we're going to get 1. And so you can think of this vector field here as sort of an on-off switch, if you will, that just determines whether a curve goes around the origin or not. That's the only thing that determines its value, is whether or not it goes around the origin. And while that's cool enough, we can in fact extend this to a theorem even more broadly. And here, this is called the winding number of a curve. So take any curve that does not contain the origin, a closed curve, let's say, that does not contain the origin. Because of this phenomenon, we see that the line integral will exist as long as we don't cross through the origin here. But in fact, the answer we get is always an integer. That's what's pretty cool. So it's not just 0 or 1, which you've seen in 2 cases, but in fact, let's imagine a curve that goes around the origin twice, right? Perhaps it goes like this and takes some weird shape, and then it doubles around, and okay, we'll let it cross itself here, and ends up back here. Let's call this guy C. What's its line integral going to be? Well, this looks like not a simple curve, of course, but if we split it up into 2 pieces, which we can certainly do when taking an integral, say one piece on this interior piece going around here, and then here, right? You notice that that piece is going to get us 1. It encircles the origin. But then we've got the other piece here, right? You can imagine it bouncing around, still piecewise smooth. That's going to get us 1 as well, because that wraps around the origin. So in total, right, this curve is going to give us an integral on the origin for this particular f of 2. We call that the winding number of the curve. So regardless of exactly the shape it takes, this integral just counts how many times did the curve wrap around the origin. And it does it with sine. If we were to do another curve going around, say, this way, and this way, and this way, I don't have to do any computation. I know what that integral is going to be. All I have to do is just count with sine how many times does this go around the origin, and it seems to have circled it right 1, 2, 3, 4 times going clockwise. It's given us a minus sign of -4. So this is an example of what we call an invariant in mathematics. So we can take any curve that can change the shape, but as long as it goes around the origin the same number of times, the line integral is going to be the same. So we've got this means of measuring the winding number around the origin of any curve just by integrating. All right, that's it. Until next time.